I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
Roger, 0G, and I feel fine. Oh, that view is tremendous.
Nice sun, Ed. You look beautiful. I feel like $1 million. I'm going to pick up.
6 is about 10 feet above and to the left of 7. We're just flying nose to nose.
During the 1960s and 70s, a dozen astronauts made the stunning odyssey to the moon and back again.
Nearest from here is a grand oasis of the big vastness of space.
It's a nice-looking machine.
So is yours. Columbia, this is Houston, reading you loud and clear, over.
Eagle, you're looking great. Okay, all flight controllers, gonna go for landing. Retro. Go. Fido. Go. Guidance. Go. Control. Go. Telcom. Go. GNC. Go. Ecom. Go. Surgeon. Go. Capcom, we're go for landing. Eagle, Houston, you're go for landing, over.
Contact light. Okay, engine stop. Houston, Tranquility Base here. The Eagle has landed.
NASA had been responsible for one of the supreme achievements of our time.
That's one small step for man, one giant leap for mankind. Hippity hoppity, hippity hoppity, hippity hopping over hill and dale. Hippity hopping along. Ignition. Right away, Houston.
From the early days of Project Mercury and Gemini to the Apollo moon landings, the space agency launched brave men into the heavens and brought them safely home. It all seemed so effortless and so routine. The Can-Do agency had delivered on President Kennedy's bold challenge and inspired a nation. Its conquest of space stood as a symbol of American technological superiority and a testament to the seemingly unlimited capabilities of humanity.
T-minus 10, 9, 8, 7, 6.
All of that changed with Challenger.
4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. Roger, roll, Challenger.
Challenger now heading down range.
I can't characterize it as an accident at all. It's a disaster, a horrible, terrible disaster, but not an accident, because we could have stopped it. We had initially stopped it, and then that decision was made to go forward anyways.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles. Engines throttling up. 3 engines now at 104%.
Challenger, go with throttle up.
Roger, go and throttle up.
One minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles. Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
I will never forget where I was when I found out about Challenger. I remember being absolutely stunned by the news. I just couldn't believe it.
Professor Mark Meyer is an organizational scholar at the State University of New York at Binghamton. As one of the nation's leading experts on Challenger, he has devoted 5 years of intensive research to the tragedy.
I think it's safe to say at this point that unfortunately this thing really didn't come out of the blue. It was really an accident waiting to happen. You know, as one of the launch officials told me that, and this is a direct quote, we were lucky, just dumbass lucky, you know, that we hadn't had a disaster like this before.
In its final report, issued June 6, 1986, A presidential commission concluded that the disaster was caused by the failure of a rubber O-ring on one of the Challenger's booster rockets to seal properly, due in large part to freezing temperatures before liftoff. But the commission also identified serious flaws in the launch decision-making process and pointed out that this was a disaster waiting to happen, an accident rooted in history.
Once you know the whole story, you know, the tragic bottom line just cries out at you that these 7 people didn't have to die. You know, that this could and it should have been prevented.
The roots of the Challenger disaster can ultimately be traced back to the early 1970s. What could the space agency do that could compare with the dramatic success of its Apollo program? Funds were drying up, and plans for a space station and manned missions to Mars were indefinitely postponed. The reusable space shuttle, originally intended to play a supporting role as space ferry to the station, now was thrust into the spotlight by NASA. Wary of mounting budget deficits fueled by the unpopular Vietnam War, a reluctant Congress and a skeptical Nixon administration were sold by NASA's portrayal of a system so reliable and competitive that it would ultimately be a moneymaker for the government and guarantee jobs for political constituents from coast to coast.
The United States can no longer afford the luxury of the throwaway rocket. Our answer to this challenge is the Space Shuttle, the world's first reusable spacecraft. To get some idea of the savings involved in terms of $1980, it costs about $22 million to put a single satellite into orbit on a Delta launch vehicle. The cost of putting that same satellite up on a shared shuttle mission is between $8 to $12 million, a savings of from $9 to $13 million.
The problems of building a new spacecraft are almost inconceivable in number, and they begin in the process of planning, a process equally as important as the construction itself. Regular telephone conference meetings between the shuttle program management and the contractor have improved communications and helped reduce traffic. Tiny, persistent, seemingly insignificant problems must be resolved in a slow but necessary process to prevent or resolve larger, more difficult problems.
The space shuttle is about to enter its orbital flight test phase. Once this is completed, the shuttle will begin operational missions. The users are standing by. Space in the payload bay has been reserved for the first 3 years of operation by the United States and foreign government agencies.
The reusable space shuttle vehicles are designed to fly up to 60 missions a year. They will be launched like a rocket and land like an airplane.
The shuttle program was almost made up out of the whole cloth. There is nothing in its original specifications that has come anywhere near reality and performance.
Robert Holtz was editor of Aviation Week and Space Technology and a member of the Presidential Commission which investigated the tragedy.
They had the illusion that the shuttle would be a space airliner, a cargo truck with a regularity and economy that time has proved was a grand illusion.
The stage is set for a new era in spaceflight for NASA, STS, the Space Transport System.
Breakers closed.
5, 4, we've gone for main engine start. We have.
It is the first of 4 orbital test flights for the shuttle. A marvel of scientific achievement, the Columbia is launched again, and again, and again. The STS-4 mission is sent on an extra orbit so the President can arrive in time for the landing at Edwards Air Force Base in California. Thousands are on hand to celebrate the occasion.
Than the typical 4th of July fireworks display could ever hope to equal. The 4th landing of Space Shuttle Columbia, world's first reusable spacecraft. Columbia's first landing on a concrete runway, officially ending the orbital flight test program. Takeoff of the second orbiter in the shuttle fleet, Challenger, on its ferry flight to Kennedy Space Center, Florida, to be launched into space in the early part of 1983. And with Shuttle Pathfinder Enterprise as backdrop, the announcement of America's new space policy by President Ronald Reagan.
Beginning with the next flight, the Columbia and her sister ships will be fully operational, ready to provide economical and routine access to space for scientific exploration, commercial ventures, and for tasks related to the national security. We've only peered over the edge of our accomplishment.
Looking back at that spectacular event and the performance of Space Shuttle during its first 4 flights, there seems little doubt now that it is a reliable, reusable space transportation system. It is projected that by the mid-'80s, there will be 2 shuttle launches per month. Only the shuttle has that capability. It meets a need, providing access to low Earth orbit on a routine basis. By launching on time, serving as a platform for Earth observation.
And there was also a political dimension to it as well, because the shuttle had been sold as a reliable space truck.
Richard Cook was a program analyst in the budget office at NASA headquarters at the time of the Challenger disaster.
And it had been declared back in 1982 a fully operational system. The White House was treating it as a fully operational system that was going to fly all U.S. Space launches eventually. And there was just a whole party line and propaganda that the thing was a completely understood, completely reliable vehicle. And it wasn't.
We have a go for main engine start. 5. We have main engine start. We have a cutoff.
NTD, we have an RSO on board.
We have an abort by the onboard computers of the orbiter Discovery.
Launches were increasingly predictably delayed. In 1983 and 84, a total of only 9 missions were flown. The space airline air cargo image which NASA had worked so hard to cultivate was a mirage. The agency had grossly underestimated the technological complexity of flying a space shuttle and overestimated its ability to surmount any technological problems which arose in the process.
Liftoff of STS-7.
Particularly troublesome was the alarming discovery, as early as the second mission, that critical rubber seals in the rocket boosters were eroding in flight. A danger which, in fact, had been predicted by NASA engineers years earlier, evidence of a fatal design flaw.
25 seconds, roll maneuver completed.
In 1973, when the contracts for the shuttle had been announced, Rockwell International was selected to design and build the orbiter fleet. And Thiokol, due principally to what NASA called its sizable cost advantage, beat out 4 competitors for the contract to develop the reusable rockets which would propel the shuttle into orbit. Thiokol had been ranked lowest in actual engineering design. The key concern with the Thiokol proposal centered on the so-called field joints of the twin solid rocket fuel boosters, designed to be reused up to 20 times. The booster is actually a stack of 4 massive interlocking cylinders, each 12 feet wide and over 25 feet tall. These giant rocket segments are loaded with solid propellant and shipped to the Kennedy Space Center, where they are assembled in the field, hence the name field joint. The so-called tang of the upper segment slides into the groove or clevis of the lower segment. During ignition, the solid fuel inside burns with explosive pressure. In order to prevent the hot combustion gases from leaking out, each joint is sealed by 2 synthetic rubber O-rings, each about 1/4 of an inch thick and about 12 feet in diameter, the same diameter as the booster. In theory, the first, or primary O-ring, is supposed to seal the joint. Thiokol claimed the second O-ring was a redundant feature, a fail-safe, there to serve as a backup in case the primary seal should fail. After a 2-minute burn, the boosters are jettisoned and parachuted to the ocean. They are then recovered and towed back to the Kennedy Space Center for disassembly and damage assessment by an engineering team from Thiokol. Following inspection, the segments are shipped back to Thiokol in Utah, where they are fitted with new O-rings, reloaded with solid rocket fuel, and sent back to Kennedy for use on a subsequent mission. Recovery and inspection of the boosters revealed that, in actual practice, the joints were not sealing properly. When the rockets were ignited at blastoff, a phenomenon called joint rotation occurred. In the fraction of a second it takes for the boosters to become pressurized, each segment of the solid rocket bulges like frozen cans of soda. Because the rocket is stiffer at the joints than at the segment midsections, the tang and clevis in the joint rotate. They move relative to each other. But instead of moving toward one another and sealing, as the Thiokol designers had expected, the tang and the clevis bent away from one another, precisely as predicted years earlier by NASA's own engineers at the Marshall Space Flight Center in Huntsville, Alabama. In this 1979 memo, senior NASA rocket engineer John Miller condemned the Thiokol design as completely unacceptable. Miller's tests revealed that the opening of the joint was causing the primary O-ring seal to extrude into the gap, forcing it to function in a way which violated industry and government specifications. Miller protested that the excessive tang-clevis relative movement also allows the secondary O-ring to become completely disengaged from its sealing surface. In essence, there was no reliable backup if the primary O-ring should ever fail. NASA eventually conceded this and, in late 1982, officially reclassified the joint from Criticality 1R for redundant to Criticality 1. Failure effect, loss of mission, vehicle, and crew due to probable case burst resulting in fire and deflagration. The reclassification had little apparent effect on either NASA or Thiokol, however. NASA managers, even up to and through the presidential investigation, would refer to the troublesome opening of the joint as an extrusion gap and insist that the secondary seal was indeed a redundant failsafe under all but the worst of conditions, even though no such conditions were specified in the critical items list. Flights and the consequent escalation of risk would continue unabated.
165 feet, 116 feet, lock, touchdown.
January 24th, 1985. Discovery lifts off on mission 51C, the 15th flight of the shuttle program. At the time, it is the coldest launch on record. The air temperature at liftoff is 53 degrees.
In January 1985, I was sent down to the Cape to give a presentation on the sensitivity and the design features of the joints. And while I was there, I was tasked to inspect the hardware as it was recovered from the Atlantic Ocean, as I had done in the past, and then report my findings back, which became incorporated into the flight readiness review system for the next flights.
Roger Beaujolais was a rocket engineer at Morton Thiokol and its top expert on the booster field joints.
I discovered that the 2 joints in that vehicle contained massive hot gas blow-by, and by massive I mean on a 12-foot diameter cylinder, 110 degrees and 80 degrees of arc length, which means, if you put it in layman's terms, you couldn't encompass the amount of damage by spreading your arms in trying to do so. It was much, much more than we had ever seen before.
So this was, what was your reaction to that?
One of absolute amazement that we had not had a disaster at that point in time, because we were very fortunate with that amount of gas getting past the primary seal that the secondary seal sealed it off and it worked just fine.
The O-ring problem escalated after Mission 51B, launched on April 29, 1985. In May of 1985, Beaujolais and his team inspected a nozzle joint in the booster and were shocked to discover a new phenomenon, erosion of a secondary seal. It was the worst seal failure yet. 2/3 of the secondary O-ring had been eaten away.
And to our utter amazement, we found the primary seal destroyed in that joint. And we postulated that it hadn't sealed for the first 2 minutes, the full 2 minutes of booster flight. And that really escalated the concerns, because if that scenario, whatever it was that caused that, ever occurred in a field joint, then we could have lost the flight under normal room temperature launch conditions, because that was not a low temperature launch.
Back in Utah, Beaujolais' discovery prompted him to deliver a blistering memo to the Vice President of Engineering, Bob Lund, in which he openly criticized his company and NASA's mistakenly accepted position to fly without fear of failure.
And I stated, this letter is written to ensure that management is fully aware of the seriousness of the current O-ring erosion problem in the solid rocket motor joints from an engineering standpoint. And I said, if the same scenario should occur in a field joint, and it could, then it is a jump ball as to the success or failure of the joint, because the secondary O-ring cannot respond to the clevis opening